Good day. This should be fairly straightforward. We're going to be looking at how we go from to dissociation equations, how it relates to solubility, and we want to get across the idea about the difference between solubility and dissociation. So we start off with an equation, and these are our equilibrium arrows here, just because they're easy to draw. And this is dissociation because it's splitting into its ions. It doesn't really want to do it that much. Instead of calling it KQ, we call it KSP, SP for solubility product. Now, on the back of your table of solubilities, you have a table of KSPs, and those can be very helpful. Here, we're showing Ag3PO4 dissociating. We know it is not overly soluble. And when we write out its expression, here's the Ag plus to the third power. And here's phosphate to the first power. And I forgot to point out that that's squared because the coefficient. So this is tying into what we did recently when we looked at the math of equilibrium. Notice we do not include what's on the left of the double arrows because they're solid and the concentrations don't change. So we're looking at the concentration of ions multiplying together. That part should be easy. So Ksp is the equilibrium constant for a solid dissociating or splitting into its ions. So the Sp comes from solubility product. Now solubility tells us how much of that solid will dissolve, and we can measure it in units like moles per liter, grams per liter, or grams per milliliter. Those are the common units we use. So in this PowerPoint, we're going to look at how do we go from a Ksp to solubility in these units, or how do we go from solubility to calculate a Ksp. So if we're going from Ksp to solubility, that has to be given in the question, or you'll look it up on your chart. So let's try some questions here. So AgBr on your regular table of solubilities, it'll say low solubility because it has this value in moles per liter. Now notice it said it's the solubility and it had units. Ksp being an equilibrium constant, we don't generally include units. So we're going from solubility to Ksp. So we definitely want to write out a Ksp expression. And we get that from our reaction or our dissociation equation. So there's our dissociation. Now I've gone a little crazy with the ice. We really don't need to do this. What we know is when this thing splits, it's going to split into x of this and x of that. But we're already told what the value of x is. This right here is this. It's going to be the x. So we do our Ksp expression. So there's our Ksp expression. We know that's x times x squared. And so we took our 8.8 times 10 to the minus 7, squared it, and we came up with that answer. So that's, I'm making it look more complicated than it was. In this case, it gave us the solubility, which is always going to be our value of x. It said multiply those together, which we did. It gave us this, and I just wrote it here to make it big, and I just love drawing arrows. So here we're calculating the solubility based on a Ksp. Again, we don't need the ice mumbo jumbo. This is a one-to-one deal, so we get x and x. But in this case, we have our Ksp, and now we're going to solve for x. That shows up on this slide. Hello. And I got a little carried away. So here's our Ksp expression, x squared. But this, we know, is our Ksp. So x squared equals that. X itself is going to be the square root of that. So square root of 4.8 times 10 to the minus 9, 6.9 times 10 to the minus 5, and we put in units. Solubility always needs units. And so if you don't put in a big M, it's wrong. So we start with two easy examples. Time to get a little more complicated. Again, you wouldn't bother with all this ice mumbo jumbo. This dissociates into one of these and two of these. That's why it says X and 2X. In this case, we're told that this is our solubility. So we're going from solubility to Ksp. So we're going to be plugging X and 2X in to where these appear in our dissociation equilibrium. So we write out our Ksp expression. X goes in here, 2X goes in here, and we have to square it. So it comes out as 4X cubed. And it's best to write out as 4X cubed because it cuts down on a chance of making mistakes. Now, before we do that, I should backtrack. We were given this solubility in grams per liter. We have to go back to grade 11 and think, how do we go from grams to moles? Grams per liter, moles per liter? First thing is we got to convert that to moles per liter. We divide by the molar mass of FeOH2. So once we've done that, now we have our solubility, and that's our X and our 2X. So we see it's 4X cubed. So we go 4, we plug this right in here, we cube it first, multiply by 4, and we get our Ksp. A lot of mumbo jumbo when I use PowerPoints, but I'll do some more handwritten examples at some point where things will be clear in terms of how I explain it, but less clear because it'll be my terrible handwriting. Now, this one, I've got the silly ice chart, don't really need it. And we have another X and 2X situation because of how it dissociates. We have a Ksp value. We're first going to figure out the solubility in moles per liter, and our last step is to convert the moles to grams by multiplying by molar mass. So let's go through our steps here. Here's our Ksp, 4X cubed. We knew the Ksp, so we solve for X. So what do? We take this number, we divide it by 4, and then we take the cube root. But that comes out in moles per liter, so we put that down here. We multiply by the molar mass of MgF2, and we get our answer in grams per liter. So I know it's a little rapid fire. Go through this more slowly or go through it again, and hopefully it becomes more clear. But we will be doing lots of examples in upcoming videos to help you get on top of this stuff. You have to dominate this stuff before we make it a little more tricky.